will be ready to go. Okay. Now, we've already done example 3, but that's the screen I'm going to write on. Did want to let you know a couple of announcements, okay? The first one's a pretty important one. Now, while y'all were off all last week, we had meetings Monday and Tuesday and then office hours on Wednesday, those who didn't choose to take time off. And in those meetings, one thing that was really, really stressed hard was student course evaluations. And one of the reasons for that, we have a SACS visit coming up in the next few years. Probably all of you will be gone from here by the time it gets here, so it won't be influencing you directly, but kind of indirectly it does in the fact that we need to have lots of good data because they look several years prior to their visit to see that you don't just put together a real nice package for them to come. They look and make sure you've been doing this all along. And our numbers on student course evaluations, our percentages, have been dropping fairly steadily, okay? And I guess we just haven't put enough emphasis on them. They say that's one of the things they really will look at. I think we're down less than 50% participation, or we have been. They want 80% participation. So that means every one of you, because there's a bunch of people not here yet and a bunch of people who aren't here, we need those student course evaluations. Now, I use them to look at areas that I need to improve. I use them on a department chair. I use them in every evaluation I do of my instructors, so they really do get paid a lot of attention. But you see, I get to see and interact with you every time we meet. The folks like in admissions and registration, library, bookstore, those kind of areas, they really don't always get the feedback that I am able to get, so they really need theirs. So when you're asked to do a couple beyond maybe your classes you're taking, please do those too. Give us a fair shot. I mean, give us exactly what you're thinking. We're not asking for anything great. Tell us what it is. That way we can improve. So please, folks, do the student course. How many have done them so far? All right. Good representation. Those who haven't, please do those. You do have, I think, until a little bit after finals to get them done if you want to see your final grade. But here's the problem with that. I know when I was a student, when that last final was taken, I turned it off and I was heading home, So I would not have thought to go back and, I need to do my student course evaluations. So please do them now rather than forget them. But if you're sure you'll be able to remember, that's fine too. But I think most of you have a pretty good idea what you're going to say anyway, so why put it off? Go on and get the student course evaluation done. All right, one other announcement, and this one's not as important as that one, but just to let you know. Normally on Fridays, I have office hours on the Birmingham campus, 7:45 to 11:45. Not this Friday. I've got an infusion this Friday. I'll be at the Perkins Clinic before 7 and probably till after 4:30, and then I'll drive home and go to bed. Okay, so it's not going to be on campus on Friday. All right, any questions on anything we've done so far? Okay, we're going to wrap up 2.6 today. Then we'll start 3.1, and Thursday we'll have the test on Chapter 2. It'll cover the first 3 sections that you were quizzed on and the last 3 sections which you haven't been quizzed on. So be prepared for that. Formula and equation sheet. Be ready. Bring calculator, scratch paper, whatever. Okay? Graph paper if you prefer your own. I'll have graph paper if you want to use mine. But if you like yours better, you can certainly bring that. Any questions then before we get started? All right, now, was I right? We're on example 6. Is that what your memories were? It's been a long time. Lots of turkey between the last time we met, right? I think it was example 6. So I'm almost certain we did example 5. So example 6 says to sketch the graph of, this is not a great slide for doing that. That's a better slide. Sketch the graph of, oops, Let me get my pen set up. Okay. F of x is equal to x squared minus 9 over x squared minus 2x minus 3. All right, I think I wrote it right. Sketch the graph of that, and it doesn't say state the domain, but we can do that if you want to. Okay, where would you begin? Find an intercept. Okay, how do we find the intercepts? Okay, a good thing. One of my favorite sayings is, and I've said it in several of the applications we've had so far, and I think this is one that is particularly applicable to, factor everything in sight. Okay, let's start by doing that. Does that numerator factor? How? X plus 3 times x minus 3. Very good. That's called a conjugate. Okay? Conjugate pair. Okay? How about the denominator? Does that factor? Well, I don't know. That may take a little more work. You say x minus 3 times what? X plus 1. That's a very good factoring job there. Okay? Check it. X times x is x squared. Plus x minus 3x is minus 2x minus 3. Perfect. Now, what do you notice? Yes, x minus 3 is a common factor that you can divide away. Now, didn't want to shut down Danielle, but you see, she said find the intercepts. If you had started to find the intercept, you look at the numerators, okay, the x-intercept anyway. And if you just looked at that and said x equal 3 is a 0, then you would have put an intercept there. That wouldn't have done you in good stead because it's not, okay? That got divided out, and we're going to see what happens to that a little bit later, okay? So let's go back to Danielle's idea of now doing the intercepts. How do you find the intercepts now? Always factor first if you can. See if something like this will happen. Now, what would be your intercepts? Set the numerator equals 0, and what do you get? X equal negative 3. Don't forget the other part. So x equal negative 3 is going to be an intercept. Of course, you set the numerator equals 0, which is your f of x, which is your y is equal to 0. So that's going to be 0, negative 3. Right there is an, wait a minute. It was wrong. Okay. Negative 3, x was negative 3, and y is 0. So this first one I did was wrong. Okay. Might need some more points there, but I'll do them now. Okay. All right, that's one intercept. An x-intercept is negative 3, 0. That's maybe over here, say x-intercept, negative 3, 0. You set the numerator equals 0, which made f of x equals 0, which made y is equal to 0, and you found x to be negative 3. You think you'll have any other x-intercepts? Say again? No, because you canceled out the other possibility. Okay, divided it away. So yeah, it's not going to be. That's our only x-intercept. Think we might have another one? Oh, come on. What other, if you don't have an x, you might have a y. How do you find your y-intercepts? Yes, put 0 for the x's, okay? And let's do it for our canceled form here. And if you put 0 for the x's here, what do you have left? 3. So y is equal, alpha vector y is equal to 3. So 0, 3, that's up here. All right, we have 2 points. What do we want to try next? Say again? What point? I wouldn't. I would do my asymptotes next. Okay, how do we go about approaching the asymptotes? You don't touch them. Okay, never mind. I'm just kidding. How do we find the asymptotes? There's 2 of them. 2 possibilities. Pick one. Vertical. How do we find our vertical asymptote? The vertical asymptote is going to look something like this, or this, or this, or this, or this. What's that telling you? All right. Not where x equals 0, but where... No, not where y equals. Those are your intercepts. We did those. I didn't write down the second one. Y-intercept is 0, 3. Okay? What is your vertical asymptote? It will be a hint. Your x-intercept you got by setting the numerator equals 0. Ah, yes, let's set the denominator equals 0. What will that tell you? When can the denominator be 0? Never! Okay? So that's going to do, if there's any value for x that makes that denominator 0, that function cannot touch it. That's what the vertical asymptote is. Any value that would happen to? Okay, x cannot equal -1. So our vertical asymptote is x cannot equal -1. Because you set that denominator equal to 0, or not equal to 0, and then subtract 1 from both sides, you get x not equal to -1. So here's your -1, and just for the funsies, I'm going to, -1's here, I'm going to make this red, meaning don't touch it. Don't go there. Too hot to handle. Okay. Now, we've got our horizontal asymptote. Let's go back to dark. Okay? Vertical asymptote. What are we missing here? Say again? Horizontal asymptote. How do we find it? How do we find it? Oh, it was a long time ago. But Tef made it. Okay. Horizontal asymptotes. What is that talking about? End behavior. And what do we look at for end behavior? Say again? Yes, it has to do with the leading coefficients. And in this case, this is rational function, so we look at the ratio of the leading coefficients. So what's the ratio of the leading coefficients? They're actually not leading coefficients, one leading term. 1. So horizontal asymptote is y is equal to 1. That's our end behavior. You want that in red too, just to keep the asymptotes the same? Okay, well, let's write it down first. Horizontal asymptote is y is equal to 1. Ratio of the leading terms. So we'll put that in red too, since we're doing asymptotes in red. And it's Christmas, why not? Okay, so this will be the horizontal asymptote. Okay. Now, guess what, team? This is one time we really don't need any, not quite any. We hardly need a test point. Because you see this point here tells you you'll approach a horizontal asymptote in your end behavior, and the vertical asymptote, you can't touch it all. Okay? So you know that's going to be like that. And I can draw that part in right now. Okay? I don't need a test point except maybe to help me see where it goes, how it gets there. I don't draw well. Any extra points would be helpful. Okay. Now, I said almost. We have something in this quadrant too, which means it's got to be going up and it's got to be going out. Okay? But we have that one little issue. What's the first thing we did after we factored everything in sight? You canceled out the x minus 3, right? But guess what? This x minus 3 was originally in your denominator. So you know the function cannot be at x equal 3. Okay? But you see, there's nothing in what's left that says x can't be equal to 3. So let's plug in a 3 and see what we get. X equals 3. What will that be? 6 over 4. What's 6 over 4? 3 halves. There you go. Oh, you said that. I wasn't listening well. Okay, so x equals 3, and 3 halves is 1 1/2, right there. But guess what? It can't be there. So I put a hole there. It cannot be there, because that would have made your denominator 0. But other than that, the function is doing this and that. Okay? You just can't be there. Okay? So that's what happens when you have a common factor, numerator and denominator. If that has a 0, that denominator does, even though it doesn't give you a vertical asymptote, it does give you a hole in the function. So you leave a hole there. So that's sort of the new thing. We did, I think maybe our first example did that, or one of the early ones, and now this one does. So that's what the graph looks like. Make sense? Now, if these 2 points would have wound up in the same quadrant somewhere, yeah, then you have to do some test points. Okay? But since this one's over there, that one's up there, you have no choice but where they go, except for x can equal 3. So whatever the value is at x equals 3, when you plug it in there, that is your hole in the ground. Like the hole in the wall game. Now, y'all are too young to remember that. Butch Cassidy and Sunday School. Never mind. Okay. Any questions on that? They did some test intervals and did some representative test points. And you see, if you look at their illustration, you see, boy, they did a lot of them too. But they didn't get much better precision than what I did. I mean, my line looks terrible, but that's my drawing. All right, there is a checkpoint well worth your effort to take a look at the checkpoint. Okay, the next subsection here is on slant asymptotes. Pretty interesting things, but we just don't have time for them, okay? I wish we did, but let me give you a hint. A slant asymptote will never replace a vertical asymptote. That's where your denominators are 0, right? Can't have that, okay? But your slant asymptotes kind of take the place of the horizontal asymptote. Now remember, the horizontal asymptote is either a number when like we had here, when the leading terms have the same degree, the ratio is going to be a number. If this were a x squared down here and that was x up there, then the ratio of the leading terms would have been 0. That means the x-axis would be the horizontal asymptote. Okay? But if the numerator had been an x squared and this would have been an x, then we would have said no horizontal asymptotes would be absolutely correct. But in that case, you would have had a slant asymptote. A slant asymptote happens when the numerator has a degree 1 greater than the denominator. If that would have been a squared and this is x, then you would have had a slant asymptote. What you do to get that? Divide this into that. See what you get. plot that, that's your slant asymptote. We're not going to do that. That's what our slant asymptote is. If that was 2 more than this one, nothing at all. Nothing you can do. We don't talk about any asymptotes there. So we're going to skip those, but let's move on to applications. Let's do the application. I think last time I said we would, this is a previous problem, example 3. Okay, we're skipping slant asymptotes. There's the information if you want to read about it. And so notice here, this one has a slant asymptote because the ratio of leading terms is x. Okay? So what you do is divide this into that. And that gives you a line. And that's your slant asymptote. Okay? We're not going to do it, so don't sweat it. There's that line. And you divide this into that. You could use synthetic division there, right? Because it's coefficient 1, exponent 1. So you can divide that, and when you get this part, forget about the denominator, that's your line. Y is equal to that quotient part. That gives you your slant asymptote. Fun stuff to do, but we just don't have time. And this is one just like it. Okay? Of course, the first thing I would do would be what? Say again? Well, even before that, what's my rule? You weren't in here when we did it. Factor everything in sight. Well, the denominator won't factor. I'd factor that numerator just to make sure that we don't have anything canceling out. We wouldn't. That's okay. So so you would divide next and see what your quotient is. That gives you slant asymptote. But you don't have to do it next. You can do your x-intercepts just like we did before, the y-intercepts just like we did before, the vertical asymptotes just like we did before. But this one doesn't have a horizontal asymptote, so you divide to get the slant asymptote. And when they factored it there, that gives you the x-intercepts, x equal 2 and x equal -1. Your y-intercept, your vertical asymptote is x not equal to 1. So you got that. But when you divide, you just get an x. That's the identity function going right through the origin. So that's your slant asymptote. Okay, you did the y-intercept. You could plug in x equals 0. That was easy. I wanted to point something else out to you. I don't know if this is helpful to you. But when we were saying horizontal asymptotes, I should have done it back when we had that. But the x-intercept is the y-intercept when x equals 0, that's the ratio of your constant terms. Whereas your horizontal asymptote is the ratio, if you have one, is the ratio of the leading terms. So just, shows you there's a little bit of more symmetry there. Okay, so we got the y-intercept, the x-intercepts we just did, vertical asymptote we did. Did they get that right? Yeah, okay. I'll make sure they got it right. Yeah. No, they didn't. Yeah, they did. Okay. And then the slant asymptote was y is equal to x. They did some test points. You could or could not have them. It doesn't matter. Yeah, you would. No, you wouldn't need them. Because you see, you had this point for your x-intercept, that point for your y-intercept. You know it's got to be going like this. Can't touch the vertical asymptote. It's going to approach the slant asymptote in the long run. Okay? You add this one too, so you know it has to be going down this way and up that way. So you didn't need any test points. They did them, but that maybe just helps make the shape a little better. But there's your slant asymptote. All right, now for applications. There are many examples of asymptotic behavior in real life. I have a niece who's really sort of wacko. She's really funny. She's a medical doctor. She's very smart, but she's wacko. She just really is. And it seemed like it was a Christmas. We were sitting around the table, and just out of the blue, she said, "Uncle Charles, what's an asymptote?" So I started sort of trying to explain it to her. You approach it's like, "Oh, okay, yeah." So then, when she wanted to make a toast, she said, "Let's do an asymptotic toast. You approach the glasses, but you never touch. Yes, so she's wacko. Okay, so anyway, some example of asymptotic behavior in real life, okay, if you are akin to my niece. Okay, for instance, example 8, which we're going to do now, shows how a vertical asymptote can help you analyze the cost of removing pollutants from smokestack emissions. Oh yeah, that's what I wanted to do this morning. Okay, a utility company burns coal to generate electricity. Doing less and less of this these days because natural gas has turned out to be cheaper and much cleaner. Okay, the cost C, and hopefully we're doing a lot more solar and wind and stuff like that too. The cost C in dollars of removing P% of the smokestack pollutants is given by this formula. 80,000 P, where P is a percent, not the decimal form but the percent form, divided by 100 minus P. Now, certainly, as P is increasing, you're going to move more and more. This numerator gets a little bit bigger, right? If you're moving a greater percent. But look what happens to the denominator. As P is getting larger, it can't get any greater than 100%. As you get closer to 100%, this denominator gets smaller and smaller and smaller. So that's getting bigger. That'll make it really blow up. So that's what they're talking about here. Of course, P has to be something between 0 and 100. You can't have less than 0%. You can't have more than 100%. So that's going to be that. So you see, the closer you try to get to 100, the more costly it is. You're a member of the state legislature considering a law that would require utility companies to remove 90% of pollutants from their smokestacks. The current law requires 85% removal. How much additional cost would the utility company incur as a result of the new law? Okay? Well, there's nothing you really need to do but plug it in. Let's first plug in the 85. What would that give us? This will be C85. That would be 80,000 times 85, because that's the percent now, over 100 minus 85. And that would be, goodness gracious, I see 1, 2, 3, 4 zeros there. Second? That sounds about right. 1,070,000. Okay, big number. Divided by 15. Right? Someone with a calculator, plug it in, plug it in. Did you get it wrong? Someone with a calculator, multiply 80,000 times 85. What you get? 0, 0, 0. What's that? 800,000. And what did you say, 6 million? Yeah, that's what, that sounds better. 6,800,000 divided by 15. Okay, a little slower. Say again. 53,000. 333 and 33 cents, right? Okay, we got to get those pennies right. Okay, now let's do it with 90% removal. Anyone want to hazard a guess right now? Anyone give me 500,000? What would the cost of that be? Second? You think 720,000? Is that what you're guessing? 453,000 here. Huh? Second? Okay, let's plug it in and see what we get. C of 90% reduction will be 80,000 times 90 divided by 100 minus 90. This is a lot easier. 7,2,0,0,0,0, I think, right? Okay, that didn't go up too much. Went up some. But you're dividing it now by 10. So that's going to be $720,000. Whoa, okay. Didn't quite double, but came pretty close to it, just for that extra 5%. Okay? That's where policymakers really have to buckle down and earn their keep. Okay? How many people's lives would have been saved by that extra 5% cleanness? If it's hardly any, that may not be worth it. If that's a significant number, like a lot of people with asthma or young kids or elderly, yeah, then you have a tough decision to make. Okay? So, that's all they ask. How much additional cost would it be? Subtract the 2. 453. I'm hoping y'all did it right. Did they do the pennies too? Yeah, no, they didn't. They just left it like that. Okay, and that would be 260, isn't it? $66,667. Is that right? I did it fast. Yeah, I believe that's right. All right. Yo, pretty hefty amount for 5% more removal. In real life, sometimes you'll hear the term, something about the law of diminishing returns. Yeah, you can always take more out, make it a little healthier, a little better, but is it costing more than it's worth? I know in agriculture you have this. You can probably grow as many bushels of soybeans as you want, or corn, or cotton, bales of cotton, or whatever. But there gets to be a point where you go and spend more on your fertilizers and your irrigation and stuff like this than you're going to get in return. So that's the law of diminishing returns. If you're making less profit by spending more money, yeah, you're making more. If you're going for maximum yield, pour the money into it. But if you're going for maximum profit, yeah, you have to weigh the cost versus the input. And this is one of those. Is that worth it? Okay. If lots of people will be saved their lives, yeah, it's probably worth it. If very few will be impacted by that, then you have a tough choice. All right. You need to sup a little longer, or is it okay? Then we move on. Let's see how they did it. They plugged it in, 85, and they got $453,333, just like we did. When you put 90 in there, you get $720,000. The difference being $266,667. Fairly big chunk of change. Okay? And that was all, folks. See, they didn't even show a graph on it, so it shows asymptotic behavior, because what you're doing, you're approaching 100%. And the more you get there, the cost goes up and up and up. 99% would have been astronomical to reach that amount. Okay? So they didn't show a graph, but that illustrates it. All right. That's the end of the slideshow. Let's do vocabulary. Functions of the form f of x is equal to n of x over d of x, where n of x and d of x are polynomials, and d of x is not the zero polynomial, are called blank blank. Second, Sean. What are they called? What's the name of the chapter? The section, rational functions. Very good. Okay? When f of x approaches either plus or minus infinity, as x approaches a from the left or the right, x equal a is called a blank blank of the graph of L. The vertical, x equals something would be a vertical asymptote. So x equals something is vertical, y equals something is horizontal. Okay? Which may have taken away question 3. Okay, when f of x is approaching b, as x approaches plus or minus infinity, y is equal to b is a blank blank of the graph of f of x. Horizontal asymptote, you got it. Number 4, for the rational function f of x equal n of x over d of x, if the degree of n of x is exactly 1 more than the degree of d of x, then the graph of f has a blank or oblique blank. We didn't do that when we talked about it. Slant or oblique asymptote, we got it. So homework exercises here, do either 5 or 7. Both of those are on calcchat.com, but 7 is on calcview.com, and I've had a sneeze, sorry. Boy, what puny little sneeze you had. Okay. All right. Do any of the odds, 9 through 15. Oh, yeah. That's how you sneeze. Okay. Okay. All those are in calcchat.com. 15's in calcview.com. Do any of the odds 17 through 37. All of those odds are in calcchat.com. 27 is in calcview.com. Matching. So I have to go again. Okay. Sorry. I would do all 4 of those matching. They're fun. Do them. Okay, but only the answers for the odd ones are in the back. And none of those are on Calc Chat. View. They're both on Calc Chat. There you are, copying me. Okay. Then do either 43 or 45 or both. They're on Calc Chat, but not on Calc View. Do any of the odds 47 to 59. All of those are on Calc Chat, but 49 is on Calc View. Do any of the do either 61 or 63. They're both on Calc Chat, but not on Calc View. Either 65 or 67. They're both on Calc Chat, but not on Calc View. I would definitely do 69. That looks like a pretty fun problem. Or if you preferred, you could do 71 or 73. Okay, so any of the odds 69 through 73. Sorry, all this sneezing has loosened everything in my head and my wallet. Okay. Oh, man. Sorry. Okay, through 73. There's exploration, true, false, 75 or 77. So you can look at those. There's a writing one if you're interested in that, 79. There's another writing one on 81. And there's a project, Department of Defense, at larsonprecalculus.com if you're interested in doing that. We're not going to do 2.7 nonlinear inequalities. So if you think you might need that in your major, whatever that's going to be, take a look at it. If you have any questions, I'll be glad to go over it with you. Okay? It's a fairly short section, but we just don't have time for it. Okay? There's a chapter summary there, and since we did 2.1 through 2.6, some of the equations and formulas and illustrations that you might need are there. If I were doing a formula equation sheet, that may be one of the first places I would go for to see if they have what you need. You might have to go to some of the pages they refer to. Don't worry about 2.7. We'll get to do that one. Anytime on slant asymptotes, you don't have to worry about either on 2.6. I'm sorry. All right. If you need some more exercises to look at or something to refresh your memory of what we did earlier, and again, the odds are in calcchat.com. Number 1's a good one to look at. This is on page 190 and following. Any of the odds 3 through 7, 9, 11, either 13 or 15 or both. Either 17 or 19 or both, and 21.
Oh, I'm sorry. 1, 3 through 7, and 9, those are in 2.1. In 2.2, 11, 13 or 15 are both, 17 or 19 are both, and 21, those are in 2.2. 2.3, long division polynomials, 23, 25, and 27. 2.4, the complex numbers. You don't have to worry about those too much unless you just want to review those on your own. We didn't really go into that in great detail. So you can sort of forget about 2.4. I forgot we skipped that. Or, sorry, I didn't give any assignments in that. Okay, sorry. 2.5, zeros of polynomials, 41, 43, 45, 47. And 2.6, 49, either any of the odds 51 through 57, and 59. However, if you have any slant asymptotes, don't worry about those. Okay. The chapter test is on page 192. And again, the calccheck.com has the tutorial help for the odd number, worked out solutions for the odd number exercises. However, in the back of your book, okay. Well, you're going to have to look at yours. I think mine's different. I believe your back of your book has odd number answers, okay, on everything except okay. You'll have to look. Mine's in the teacher's edition. I don't think you have even number answers in the back. I do, but you don't. Sorry about that. I don't think. Do you? Does your back of the book have even and odds or just odds? Okay. Look at review exercises. Is that still just odds? Okay. How about chapter test? I think that's all of them, isn't it? Even and odds? Is it? Yeah. Okay. So the chapter test, you could do any of those. The answer's in the back. However, if you want to use CalcChat, only the odds will be on CalcChat. So, again, any of the ones 1 through 9, no, 1 through 7, because the others have the complex numbers. I think 12 and 13 you can probably do. 14, 15, and 16 you can probably do. You don't need to worry with 17 and 18. All right, if you're interested in proofs, there's proofs for remainder theorem and factor theorem there. Linear factorization theorem and factors of polynomials. So plenty to do there if you're interested. Problem solving, some more help there as well. All right, any questions? Chapter 2. Let me get you here. Is it? Yeah, Jalen, that's what I was going to ask. Okay. And anyone else come in since I called roll? Okay. Sorry, my nose is now like a fountain. About this folks. All right. Okay, let's move on to Chapter 3. Now, I had a question earlier. Chapter 3 is not on your test Thursday, but it will be on the last test you have. So what we're going to do, we're going to cover this today. We're going to cover it next week, Tuesday and Thursday of next week. We'll get as far as we can. And then your last chapter test will be a very short test on Chapter 3. And then your final exam will be comprehensive. It'll also be very short, and it'll cover all 3 chapters. So therefore, yes.
I'm sorry, I didn't mean to interrupt you, but at the beginning you our lowest quiz or test? What is it? Is it our lowest quiz grade or our lowest test grade?
Yes.
Is it both?
But, yeah.
Oh.
Okay. When I go to do your quiz average, okay, remember what covers the quiz average? Your research paper and your quizzes. Right now we only have 2 quizzes, and it looks like all we're going to have time for. So it's going to be your research paper and your lower quiz score. Now, if your research paper is lower than your 2 quiz scores, I might need to keep them both. I'll do whatever it takes to give you the best average. I'm not going to drop a quiz score if it actually pulls down your quiz average. I'll only do it if it pulls up your quiz average, okay? And then that quiz average will replace your lowest test score. And that would be test 1, 2, and 3. Not the final. The final is going to count. So it's 1, 2, or 3. And again, I only do that if it helps your average. Like if you do really well on all your tests, but you do poorly on the final, I'll keep them all so they'll pull the final up better. That's usually not going to be the case. Most of the time it will be your lowest test will be removed. So I don't always do it. I do it if it helps you. Okay. But the final exam will count. But it will be a shorter test, like a 1-page. It's going to be more like a quiz in length. Okay. But you got to do it in class. Okay. And that will be the Tuesday of finals week. Okay. 2 weeks from today. Yo. Okay. So. Let's look now at exponential and logarithmic functions. 3.1 is exponential functions and their graphs. If it's a big surprise to you, this book likes to deal with the graphs, okay? What we'll do is recognize and evaluate exponential functions with base A. Any base. A is any number. We'll graph exponential functions and use the one-to-one property. Now that's not the one-to-one function, it's the one-to-one property. Still pretty important. Okay, recognize, evaluate, and graph exponential functions with base E. That's going to be something new, and it's pretty helpful. And we'll use exponential functions to model and solve some real-life type problems. So let's first look at exponential functions. This will be beginning on page 198. So far, this text has dealt mainly with algebraic functions, okay, which include polynomial functions and rational functions. Now, if you think about that, what is your base always with a polynomial or rational function? The variable. And you raise it to some integral exponent most of the time. Okay, you can have fractional or decimal exponents, but most of the time, the base is the variable and the exponent is the number. Okay? In this chapter, we'll study 2 types of non-algebraic functions. These are called exponential functions and logarithmic functions. Now, why these are called non-algebraic, these are, another name for that is transcendental functions. And what we have here, the base is a number, and the variable is the exponent. And that variable can take on any value at all. It doesn't have to be an integer or a rational number or anything else. Any real number. In fact, it can be complex numbers. We're not going to do those. Now, your A always has to be greater than 0. We don't have your A, your base, being negative. And we don't have it being 0. If it was 0, that's meaningless. That's the 0 function. The A also cannot equal 1, because if A was 1, the answer is 1. Okay, so that's not very interesting either. So A could be anywhere between 0 and 1, but neither 0 or 1 or anything greater than 1. Whereas X, any real number. Any real number. Positive, negative, fraction, decimal, rational, irrational, any real number. Okay. The base A equal 1 is excluded because it yields f of x is equal to 1 to the x, which is always 1. That's not a very exciting function. Okay? That's a constant function, not an exponential function. It's an algebraic function, not a transcendental function. You have evaluated a to the x for integral and rational values of x, like I said. If x was an integer, you've done that. 7 to the 3rd power, yeah, you can do that. Okay? Even for rational values, 7 to the 1/2 power, that'd be the square root of 7. 7 to the 4/3 power, would be the cube root of 7 to the 4th, okay? So yeah, you can do those. Those are rational. For example, yeah, this is the same thing I did. 4 to the 3rd power is 64. 4 to the 1/2 power is 2, okay? Those are rational exponents. But when you have x being a real exponent, we haven't done that. However, to evaluate 4 to the x, for any real number x, you need to interpret forms with irrational exponents, which is pretty interesting to do. And most of your calculators will do this if you have the fancier calculators. Even scientific calculators will do it. The little cheapies that add, subtract, multiply, divide, they're not going to do it. But anyone that has, a scientific or higher calculator will do those. Okay, for the purposes of this text, it is sufficient to think of a to the square root of 2. There's an irrational number where square root of 2 is approximately equal to 1.414213556. That's just a round off. That square root of 2 goes on ad infinitum with never a pattern repeating itself. It looked like it's 1414, but it's not, because after that it's random numbers. As a number that has successively closer approximations, we can start with looking at a to the 1.4, then look at a to the 1.41. These are all things you can do on your calculator. A to the 1.414, a to the 1.4142, a to the 1.41421, and keep on going, and you'll get a number closer and closer to what that is. Okay? After a while, the more digits you have here, you can't tell any difference in your answers. That's going to be close enough. Usually 3 digits would be close enough, but we'll see. Okay. So, pull out your handy-dandy calculators. And by the way, if this isn't enough to bring your attention to the fact, on this next test, which will be part of your final exam on that 2 weeks from today, will have the first part, a Chapter 3 test, very short, and then the second part will be a comprehensive part. Again, very short, but it'll have questions from everything we've covered in the 3 chapters. Okay? So if you got a calculator now, try this. And bring your calculator. You should have to every test, but you've got to that last test. You've got to. Let's do 2 to the negative 3.1 power. Does everybody know how to enter that on your calculator? If not, I can help show you, I think, if you have a decent calculator. A to the negative 3.1 power. While you're doing it, let's just think about it a minute. What would be 2 to the negative 3? No, 2 to the negative 3. 1 over 8, yeah, which would be 0.125. So this is going to be something pretty close to 0.12 or something like that. Okay? So plug it in and see what you get. If you don't have a calculator, look on with someone, or 0.116. Is that what you said? Yeah. Pretty close to 0.12. Yeah. Okay? How about this one? F of x is equal to 2 to the negative x, but x equal pi. So that would be 2 to the negative pi. Well, guess what? That's not going to be far off from what you just had. 1.1 something or another, because pi is 3.14. That's 3.1. So it's not going to be far off from that. So, but you got a pi key on most calculators, right? Now, the little cheapies don't have it, but if you have the scientific or better, you've got a pi key on it. What do you get when you put that in? 0.11 second. 1123. 33. Okay. So there you would have that. Not far off from that. How about this one? 0.6 raised to the 3/2 power. Now, if I were putting that in my calculator, I would be 0.6 to the 1.5 power. Just easier to do. But you can do it 3/2. 0.6 to the 3/2 power. Well, let's think what that is. 0.6 cubed would be 0.216 or something like that. And then take the square root of that. That's going to be something like 0.4 maybe? I don't know. Do it and see what you get. 0.6 raised to the 1.5 power. Or the 3 halves power. Anyone got a calculator? Won't work? 2nd? 0.464. Okay, I was thinking it was close to 0.4. Okay. Pretty good, huh? Here they did it. And this shows you how to do it on some calculators. Not all calculators. If your calculator has this caret key, that's your exponential key. Okay? So enter the base first, and then your exponential key. Now, if you have a calculator with a minus sign in parentheses, that's the negation key. The minus sign when not in parentheses is subtraction key. Don't use that one for the change signs. Okay. Now, if you have an older scientific calculator, you may have a sign key that says plus minus, plus slash minus. If you have that key, and the really old calculators is CHS, change sign. I don't see those anymore much at all. But if you have either one of those, you have to enter the number first, then you do the plus minus. If you have the negative in parentheses, you enter that first. It's just the old way of doing that. But anyway, they got 0.1166, just what y'all said, right? Know your calculator. That's why I say, get used to it. Work on some of these homework exercises. You don't want to come into the final, that last test, and then say, how do you do this on my calculator? Do it now, okay? Learn how to do it now, okay? The second one is 2 to the minus x, but x is equal to pi, is 2 to the minus pi, which is almost the same as that. 2 caret, the negation key, either that or there, that's the negation key. If you have the plus minus key, you enter pi first and then plus minus. But then pi, you'll find that somewhere there. And that's not far off, because that's 3.1, this is 3.1416, blah, blah, blah. So, those are pretty close to the same. Make sense? Okay. And they're pretty close to 1/8, which would be 0.125. So not far off. And then f of x, f of 3 halves, if that's 0.6 to the 3 halves power, you could do it like they say here, 0.6 raised to the open parentheses 3 divided by 2 close parentheses. Okay, then put enter, you'll get your answer, like you said. Easier to do 0.6 caret 1.5. Because that's what 3 halves is, 1.5. Enter. So much easier. 3 keystrokes rather than 5. And I'm lazy. I'm really lazy. If I can get by with 3 keystrokes, I'll do it. Not do 5. I'm really lazy. Okay. Make sense? Get to know your calculator and use them well. All right, that was example 1. Okay, they're skipping example. No, they're not. Okay, here we are. Graphs of exponential functions. On the same coordinate plane, sketch the graph of each of these functions. Now, these are pretty easy ones, not 0.6s and pi's and things like that, but really easy. F of x is equal to 2 to the x. All right, so let me get my handy-dandy. Whoa, I forgot. When I went to a new section, I had to reestablish. All right. Yes. Oh, sorry. Yes. Oh, yes.
You said that this test that we're about to take, is this going to be part of our final?
Okay. The one we're taking Thursday, the Chapter 2 test, is just a Chapter 2 test. You'll have all period to do it, hour and 15 minutes. Okay? It'll be a 2-page test, about like your others have been. Like the quiz was 1 page, this will be 2 pages, so like 2 quizzes. First page is similar to your first quiz. Second page would be the last 3 sections. Approximately. They may overlap a little. Okay. Now, the Chapter 3 test. Chapter 3 is not on the test you're taking Thursday. We're going to do Chapter 3 now. We do Chapter 3 Tuesday. We do Chapter 3 Thursday. However much we get covered there, that will be the first part of your final exam. Just Chapter 3 test. It will count as a test. And then the second part will actually be the comprehensive final. And that's just going to be a one-page. It's kind of like a quiz, but only going to be questions from all 3 chapters. Probably 4 questions from Chapter 1, 4 from Chapter 2, and 2 from Chapter 3, or something like that. So I'll try to keep it short and really sweet. Okay. All right. Got it? Does that answer?
Now, I want to change something here, and it's just because I know about it. I'm going to erase this line. Ooh, I didn't, did I? Okay. I'm going to bring it down to here. The reason I knew that,
this thing is never negative, is it? If you're raising a positive number to a power, of even a fractional power, it's going to be something down here. Number greater than 1 is going to be up there. Yeah, this is never going to be negative, so I can take up more space here.
all right, let's tick off a few points here. 1, 2, 3, 4, 5, 6, 7, 8. We won't need all those. Negative 1, 2, 3, 4, 5, 6, 7, 8. We won't need any down here, but I'll put 1 for good sake. 1, 2, 3, 4, 5, 6, 7, 8. Give me some x's. 0. What's 2 to the 0? 1. All right. How about 1? 2 to the first is 2. Okay. Give me another x. 2. 2 squared is 4. Another one. 2 cubed is 8. 5, 6, 7, 8. Okay. Negative 1 would be 1/2. Negative 2 would be 1/4. Negative 3 would be 1/8, and so on and on. So you see, here's how this exponential function looks. Okay?
Now, I remember back, we just barely mentioned a hyperbola. And this almost looks like a hyperbola, except it's not. Because, sure enough, this is approaching a horizontal asymptote here, y is equal to 0, but there is no vertical asymptote there. You can go out as far as you want to here. You'll be way, way, way up there, but you never have a place that you can't go any further. A hyperbola would have a vertical asymptote somewhere you approach it. This is not a hyperbola.
This is an exponential function. Now, on the same graph, what color do you want the next one? What color? Give me a color. Green. Okay. All right. We'll do 4 to the x. Give me an x. 0. What's 4 to the 0? 1. Ooh, that's the same place. About 4 to the 1. 4. That would be up here. 4 squared would be 16. Off scale already. How about 4 to the 1/2? I mean, 4 to the -1. 1/4. That would be 1/4. The next one would be 1/16. Ooh, 1/64. So this gets smaller faster down here, but gets bigger way faster up there. So this is what it looks. But guess what they both go through? 0, 1. That's going to be a characteristic of exponential functions. As long as you don't have any shifts or things in it, you're going to be going through the point 0. Okay? For a larger base, you're going to go up faster to the right and get closer to 0 faster on the left. Okay? And I think that's awfully close to, well, let's see how their picture looks. Let me erase this ink. And let's see. Oh, here they do. They did it in the same color. Shame on them. Okay, here's alpha of x is equal to 2 to the x. goes up fast, but 4 to the x goes up even faster. But over here, 4 to the x approaches 0 faster, 2 to the x does approach 0, but not nearly as fast as 4 to the x. So that's what your exponential functions, in general, are going to look like. Okay? Now, I wish we had time. I tell you a little story about exponential functions, but we don't. So maybe next time. All right. So that was example 2. Note that both graphs are increasing. There's something to notice. Moreover, the graph of g of x equal 4 to the x is increasing more rapidly than the graph of f of x, which is 2 to the x. The following summarizes the basic characteristics of the exponential functions. The domain is all real numbers. All real numbers. Exponential function can be defined everywhere. The range is only positive numbers, not even 0. So it's a parentheses 0 to positive infinity. The y-intercept is always 0, 1. Always 0, 1. No x-intercept because it approaches 0 but never reaches there. They're always increasing functions, or at least these that we've looked at so far. The x-axis is a horizontal asymptote, but there is no vertical asymptote. They are continuous, smooth, continuous functions. Always. Okay. Now, we'll pick up on this next time. Okay? So we'll do example 3 next time. All right. Any questions? Well, no. Next time we'll do the test. Next Tuesday, we'll pick up with example 3. Any questions? Good deal. We'll see you Thursday. Come with your calculators, your scratch paper, your graph paper if you want it. I'll have some. Formula and equation sheet. Be ready for the test on Tuesday. Now, I need your quizzes in. If you haven't turned in the second quiz, I got to have those in. Yeah. Yes, but you'll need to do it soon.
Yes,
We're running out of time.
Like tomorrow, I get out of work at 12:30. Are you on this campus?
I'm on this campus tomorrow. At 12:30, I'm in class, but I get out of class at 3:15. Now, I have a little break between 1:55 and 2. I mean, it's only a 5-minute break. So if you wanted to come then, I can get you set up. Yeah. And if not, 3:15.
3:15.
Right. I'll be here until 5:15 at least. Good deal. Thanks for the quiz. All right, you too. Thanks.